Right, in this video, we're going to go over the first of two PowerPoints that are due for today, or we would have gone over today, rather. And what the topic we're going to talk about first is this idea of ionization energy. And ionization energy is how much energy you have to put in to remove an electron from an atom. And this is an endothermic process, which means you have to put energy in, which makes sense because these electrons generally want to stay by their atoms. So to rip it away, you'd have to put energy in to do that. When talking about ionization energies, if you're removing valence electrons, you remember valence electrons are those in the highest energy level. Those are easiest to remove. And as you go further and further in, it's harder and harder to remove electrons. You also have different ionization energies called the first ionization energy, second, third, fourth, so on and so forth. And these are just what or how many electrons have you removed, I guess is the best way to put it. So the first ionization energy is the energy it takes to remove one electron. The second ionization energy is the energy it takes to remove a second electron. A third ionization energy is the energy it takes to remove a third electron. And if we look at trends in ionization energy, or at least the first ionization energy, what we see is that generally, as you move from left to right across the periodic table, the first ionization energy goes up, which makes sense. If you remember on Wednesday, we were talking about the first column of metals and how to get a full octet, these atoms actually want to remove electrons. So these form +1 ions. So it makes sense that they would want to lose electrons. While the halogens, under normal conditions, they have 7 valence electrons. And so they want to get one more valence electron to have a full octet. So it would take a lot of energy to remove an electron from the halogens because they don't want to remove electrons, they want to gain electrons. And as you go up the periodic table, ionization energy increases as well. The idea there is the bigger your atom is, the further away your valence electrons are from the nucleus, so the easier it is to remove an electron. So ionization energy, right? The easiest molecule to remove an electron from is CS. The hardest is helium. You have to put in a lot of energy to remove one electron from helium. So that's our trend here. Left to right, it increases. Down the bottom, it increases. So here I have two questions to just order ionization energy. So what I want you to do is pause the video, get out your periodic table, try to put these in order, and come back when you have an order. And I'm going to do this right now. So I have my periodic table. So the biggest atom and the furthest to the left is indium. So this is going to have the smallest, followed by silicon. Excuse me. Sorry, I had to sneeze there. So silicon, nitrogen, and fluorine. So this is going from bottom left to top right. So low to high. Here, I'm just asking for decreasing, so from high to low. So we're going to start at the top right and move our way to the bottom left of the periodic table. So this should be chlorine, then sulfur, tin, lead. Again, I'm just going from top right to top left. Remember, high ionization energy means it's hard to remove an electron. Low means it's easier. So we looked at the trend of the first ionization energy, and that's across different atoms. Now let's look at the trend of successive ionization energies within the same atom. And in general, every time you remove an electron, it becomes harder and harder to remove another one. The idea there is this. Let's say you have 10 protons, 10 protons, 10 electrons in an atom, right? The positive and negative charge is the same. So that's all good. And you have a neutral molecule. Let's say you remove one electron. So you do the first ionization energy. Now you have 10 protons and 9 electrons. Overall, this has a charge of +1. So these 9 electrons are now an area of overall positive charge. They like that. Opposites attract. So if I want to remove another electron, I would have to put in more energy. So this is first ionization energy. This is second ionization energy. I would have to put in more energy to do that. And then I'll end up with 10 protons, 8 electrons. Now I'm +2. And the electrons don't really want to leave. And it will take a lot more energy to remove another electron. And in general, when we're looking at valence electrons, that is electrons in our outer shell, the removal of electrons is regular, right? So if we look at phosphorus, right? So the first ionization energy, takes 900. Then it will take an increase of 1,000. That's what I meant by 900. Take from 1 to 2 is an increase of 900. From 2 to 3 is an increase of 1,000. From 3 to 4, 2,000. From 4 to 5 is another 2,000. So all of these in the blue where are valence electrons. However, if you look at ionization energy 5 to 6, you got a jump of 16,000 now. And that is because removing the 6th electron is you're trying to remove a core electron. So just to make sure we're on the same page, what I was talking about there, let me do the electron configuration of phosphorus. It's 1s2, 2s2, 2p6, 3s2, 3p3. So our highest energy level is the 3rd energy level. And phosphorus has 5 valence electrons. So that's why in the blue, we had 5 numbers in the blue. These are the energy for moving electron 1, 2, 3, 4, 5. And it increases regular. Once we remove 5 electrons, we are now in what are called the core electrons. So these were core, these were valence. A core electron is anything that's not a valence electron, and it's very hard to remove core electrons. And we see this large energy jump in ionization energy when you try to remove a core electron. So let's try and predict where our jump in ionization energy is. That is, this is really asking between what ionization energy will we see a large spike? Or another way to think about this is how many valence electrons are there? So pause the video, try this out, and then come back when you have it. But I'm going to jump right into it now. So I'm going to just write out the electron configuration. So beryllium 1s2, 2s2. Nitrogen 1s2, 2s2, 2p3. Oxygen 1s2, 2s2, 2p4. Lithium 1s2, 2s1. So I'm going to underline the electron, the energy level that's our valence electron. You notice here it's always 2, but hopefully by now you realize it's not always 2. It depends on the element. So for beryllium, we can remove 2 electrons, 2 valence electrons, and then we're into the core. So our jump happens at ionization energy 3. If we looked at ionization energies, ionization energy 3 would be very big compared to 1 and 2. Nitrogen would be ionization energy 6. We have 5 valence electrons, so the 6th electron we try to remove would be very hard. Oxygen is 7 because we have 6 valence electrons, and then lithium is 2. So the jump is the number of valence electrons plus 1 because you're trying to remove core electrons at that point. And with that, that's the end of this PowerPoint, and I will see you in part 2.